Inferences for two population means using paired samples. So we've already looked at the means of two populations for independent samples, and we looked at it for those that have the same standard deviation and those that do not. But of course we have another type of data, a paired sample, and this may be appropriate when the members of two populations have some sort of a natural pairing to them. Each pair in a paired sample consists of a member of one population and that member's corresponding member in the other population. And how do we know really if samples are dependent or independent, or whether they are, considered to be paired? So when comparing two populations, there are two types of samples. They are dependent or independent. If the same source of data is used to obtain the data, we have dependent samples. And to define source, it's a person, object, or anything else that yields a data value. When we've got two unrelated sets of sources, they are independent samples. So in a paired sample, these are dependent on one another. The paired t-test is super applicable in the healthcare context. So I'll give you some examples of where you would use paired t-tests. So for example, before and after measurements. So say you have an individual that it's the same person and you're going to measure them twice. So before their diet and then after their diet. So each before is paired with the same person's after. And then we have matched subjects. So these are different individuals that are deliberately matched. So for example, you might be comparing lung capacity, and you might match one smoker with one non-smoker of a similar age and environmental background. Each pair is constructed to then be comparable. And we often see this in twin studies as well. So one twin receives a treatment, the other one does not. Twins are really interesting because they form natural pairs. And then we have things like crossover studies. And that would just be like a drug that you are taking and a drug that somebody else is taking. It may be the same drug, but you take it at a different time than the other person. So we'll just jump into it. Inferences concerning the mean difference using two dependent samples or paired samples. And I've got the sweetest little twins in the background. There are some facts that we need to understand before we can go forward. When a paired observations are randomly selected from normal population, the paired difference is called D. And so you'll see that we're using this subscript D quite a bit. And we need to understand their sampling distribution of D bar. So our main assumption here is that the paired data are randomly selected from normally distributed populations and that they are paired. And your formula card kind of does you dirty in this one because it doesn't talk about this or have very much information about what this means. So when you have, or suppose that X is a variable on each of two populations whose members can be paired. For each pair, we let D denote the difference between the values of the variable X on the members of the pair. And we call that D the paired difference variable. And you can see below, it's taking the sample mean of the first group and subtracting it from the second. So when dependent samples are involved, the data are thought as paired data. So the inference is really about the mean of the paired difference here. And so the difference between the two population means when dependent samples are used is equivalent to the mean of the paired differences. The sample mean of the paired difference is used as the point estimate. So keep this in mind because it's going to make more sense as we go through the example. And I'm going to show you where you can add some things to your formula card that is kind of missing from it. So I wanted to show you the test statistic for our paired t-test here. And so t star, and the star is just indicating this is a test statistic, is equal to d bar minus mu d over SD divided by the square root of n. And so we're being introduced to some new things. What exactly is d bar and what exactly is SD? Now this here is just the population mean still. Before I break it all down, though, I wanted to put the actual procedure in here. So the purpose is to perform a hypothesis test to compare two population means. The only assumptions here is that it is a simple random paired sample and that we have normal differences, not normal data. So we're actually going to look at the normality of the differences here. And that's where our D bar comes into play, because even though it's not written on your formula card, and I'm going to give you a formula for it as well, it is super duper important here. Everything else just remains the same. The only thing you need to keep in mind is that our DF will change again to just being n minus 1. No more complex delta calculations. All right, I'll explain all of those missing components here with an example. So this is an example about the ages of married people, and married couples are often used as paired data. So a random sample of 10 married couples gave the data on ages in years. Do the data provide sufficient evidence to conclude that the mean age of the married men differs from the mean age of the married women? So first of all, we're going to look at some of the assumptions here. This needs to be a simple random paired sample, and from the question we can tell that it is. The next thing is that the normality is actually going to be based on the difference here. So what we've got is here we've got the age of the husband and we've got the age of the wife. The difference, or D, is simply just 59 minus 53 is 6. 21 minus 22 is minus 1, and it's okay that you have negatives. 33 minus 36 is minus 3, and so on. So then we plot these numbers here on our QQ plot and look for normality. Okay, so that's one of the first things that you're going to want to do. If you're not given your D bar, you're probably going to be given a data set, and you do have to calculate the difference between them and also sum it up, because you're going to need that later on. All right, so we've got our hypothesis. Their mean age is equal, and the question just asks, is it different? Does it differ? So it's not equal here. And then we're going to perform this test at the 5% significant level, so our alpha is 0.05, and this here is our stat. It is D bar over SD over the square root of n. So what is D bar? D bar is the sum of D, which is your difference, divided by n. It's analogous to calculating an X bar or a mean. But what you do is you take all of your differences, you add them together, you get 36, and divided by n, there are 10 couples, and now we have D bar, and that's 3.6. Now, if you grab your formula card and you take a look at it, and I'm grabbing mine right now, you can probably hear it. It doesn't say anywhere on here how you calculate D bar. So if you want to add that on there, please do. I think this is where I find most of my students make mistakes with the paired t-test, because they think, oh, this is simple enough, and then they forget. But we're still missing something. We're missing this SD. What does that mean? What does that stand for? And is this on your formula card? And I actually don't know the answer to that. So I'm just going to take a quick gander, and I don't see it anywhere on the formula card. I have an old version though, but feel free to write it on there. What S sub D is the standard deviation calculation for the paired data. And so you can see here, it is equivalent to your standard deviation calculation, except for instead of using X, you're using D. So what you can see here is I've got D, my difference, and then I did what I would do for my normal standard deviation calculation, is that I squared all of those numbers here and then summed it up. And that then becomes your sum of D squared minus your sum of D, which is our 36, squared on the outside divided by 10. So it's equivalent to your standard deviation, and it's easy to calculate, but it's kind of blank on your card. It doesn't help you, so feel free to write that down as part of your process. And now that we have all of the components that we need, we can actually run the t statistic, which happens to be 3.6 divided by 4.97 divided by the square root of 10. And our actual statistic that we get here is 2.291. Now, of course, you can use the critical value approach or the p-value approach to make a decision on this statistic. And right here, we'll look through the critical value approach first. So the critical value is two-tailed here. So it's it's T alpha divided by 2, and we're using a DF of n minus 1. So make sure that you keep that in mind, that we're going to have our T alpha divided by 2 here, which turns into T 0.025. Using your DF of 9, you can find your critical value here of 2.262. What you'll notice, though, is that there is a little symbol in here. It's plus or minus. It is two-tailed, so it's both on this side and this side of our curve, and that's why we have plus and minus. This is the plus and this is the minus here. So let's look at our number 2.291, and it would fall on the number line somewhere out in here. So it falls within our rejection region, and so using the critical value approach, we would reject the null hypothesis. And we'll follow this up with our p-value approach. So remember, we've got a DF of 10 minus 1 is 9. So then you get your t-table, go to your DF of 9, and you're going to look in the table for the number that is closest to 2.291. Go up from there, and what you're going to see is that it is between 0.02 and 0.05. So it is still less than the specified significance level of 0.05, and we can reject our null hypothesis. So the interpretation here is that at the 5% significance level, the data provides sufficient evidence to conclude that the mean age of married men differs from the mean age of married women. Surprise! There's also a confidence interval procedure. Okay, so for the confidence interval procedure, of course, it is, similar in the way that we have everything we almost need already to just quickly calculate it. So the purpose of it is to find a confidence interval for the difference between the two population means, and the assumptions remain the same. And what we'll do here is look at the equation. It is equal to d bar plus or minus t. This is T alpha divided by 2. But what I've done here is I've put DF alpha divided by 2 because this is how you find that value, multiplied by your standard deviation that you calculated over the square root of n. So using the same example of the married couples, we'll do a confidence interval for it. So the only thing that you have to do is find your T alpha divided by 2 with your DF of n minus 1. So you're going to have 10 minus 1 is 9, so you'll use a DF of 9. And we have a T alpha divided by 2, so it was 0.05 divided by 2 is equal to 0.025. And so we can look in the table and we'll see that the number we get is 2.262. That's the number that will then go right here. We've got our D bar already. We calculated it's 3.6 plus or minus. So you'll do the equation twice, once to add this and then once to subtract all of this, and then multiplied by our SD over the square root of n. And what you'll get is between 0.04 and 7.16. And so let's put that into context with an interpretation. We can be 95% confident that the difference between the mean ages of married men and married women is somewhere between 0.04 and 7.16 years. In other words, we can be 95% confident that the mean age of married men exceeds the mean age of married women by somewhere between that amount of time. And I wanted to clearly give you those two formulas that don't seem to be on your formula card. D bar is the mean of the sample differences. So you have your two populations, you find the difference, you sum them up, divided by n. And this is the equation for the standard deviation. And it is similar to the original standard deviation equation, except for you're going to be using D in there. So again, feel free to write those down.